So, what is the main story we hear every day? We hear that humans have increased the amount of CO2 in the atmosphere, and that the CO2 changes the energy budget. Namely, because of the CO2, it's harder for radiation to escape from Earth, and therefore the temperature has to increase by some amount so that the radiation so that the Earth can actually emit this extra radiation and be in equilibrium. Now, if we want to predict by how much the temperature is going to increase over the 21st century, which essentially is the trillion-dollar question, right? We want to know by how much the temperature is going to increase. We need to know three things. First, we need to know by how much the CO2 is going to change in the atmosphere. And for that, we need emission scenarios. Suppose we don't do anything. Suppose we turn back to the Stone Age. We're going to emit a different amount of CO2. The next thing we need to do is to know how much a change in the CO2 changes the energy budget. The second thing you need to do is to know by how much the energy budget is going to change if you change the amount of CO2 in the atmosphere. Okay, by how many watts per square meter is the energy balance going to change? Suppose I bring in I want to heat this room. What I'm going to do, I'm going to bring in some heaters. I need to know what's the wattage, by how much or what rate of energy we're going to put into this room. The next thing we need to do, the third thing, we need to know what is the climate sensitivity, which is how to translate changes in the energy budget into a change of temperature. You can have one room which is insulated very well, and then a 1 kilowatt heater will heat the room by 10 degrees. And another room which is not insulated very well, you're going to bring in the 1 kilowatt, but the temperature is going to increase by only 1 degree. So we need to know this number, the climate sensitivity, in order to predict by how much the temperature is going to increase on Earth as well. Okay, so three things. One, by how much the CO2 is going to change. The next thing is by how much the energy budget is going to change following changes in the CO2. And the third thing is what is the sensitivity for a given change in the energy balance by how much the temperature is going to change. Okay? Since I'm not an economist and I'm not a prophet, I cannot predict by how much the CO2 is going to change. The IPCC, the Intergovernmental Panel for Climate Change, has a range of scenarios for different things. It's based on what economists think and a lot of other things. I don't think anyone predicted the 2008 decline in CO2 production because of the world recession. Nobody predicted the world recession, right? Well, maybe a few did, and then they became rich, but I didn't. So just as much as I cannot predict what happened in 2008, I cannot predict what will be in the future. Nevertheless, there are given scenarios for the emission. The next thing, the change in the energy budget, we think we understand the physics of radiative transfer through the atmosphere with the CO2. And the canonical number is, if we double the amount of CO2, you will change the energy by 3.7 watts per square meter. It's actually interesting that this thing was never measured directly. It's calculated, and there might be several problems. I know a few people who claim that it might be overestimated by a few tenths of %. Nevertheless, let's suppose we know by how much it's going, we know what is the change in the energy budget. The last thing we need to know is the climate sensitivity. And it turns out that nobody in the IPCC knows what the climate sensitivity is. There was a committee in 1979, a Charney committee that sat somewhere in Washington, and they thought and thought, and they said, we think that the climate sensitivity is such that if we double the amount of CO2, the temperature is going to change by 1.5 to 4.5 degrees. What that means is that we really don't know to predict ab initio, from first principles, by how much the temperature is going to increase over the 21st century. If the climate sensitivity is on the low side, it means that the temperature is going to increase by only a little if we say double the amount of CO2. If, on the other hand, the climate sensitivity is on the high side, then the same emission scenario will now give you a much higher temperature increase, and perhaps it would be a very bad idea to invest in real estate in Venice. But not in northern Canada. Okay, but this number, this 1.5 to 4.5 degrees, didn't change since the Charney Committee in 1979. If you open each and every one of the IPCC reports, even though trillions or maybe billions of dollars were invested in climate research, we don't know, well, those people don't know what is Earth's climate sensitivity any better than the people in 1979. Okay, so we cannot predict by how much the temperature is going to increase over the 21st century. Okay, I hope you're with me. Now, so how can people like the IPCC incriminate humans as the main cause for warming over the 20th century, and therefore that climate is very sensitive, and therefore that the temperature is going to increase by a lot? The only reason, there are actually two reasons that you find which can be used to incriminate humans. One is that the temperature, if the temperature increase over the 20th century is unprecedented, and if it's unprecedented, it must be humans or witchcraft. Now we know that it's not unprecedented. All you have to do is to Google ClimateGate, and you realize that the hockey stick, which was the basis for one of the previous IPCC reports, was in fact a hockey stitch. Like they stitched two data sets up to 1960 from tree rings and thermometer data from 1960 onwards. So we know that it's not unique. We know that, say, in the Middle Ages, there were temperature variations, say, the temperature was as high as it is today, and there were variations which are as fast. So this argument doesn't hold any water. The other argument, which can be used to incriminate humans, is the fact that if you try to take the global circulation models, the models that they use in order to simulate the climate, and simulate the 20th century without taking the human contribution into account, they find that the temperature increase is gone. There's no temperature increase, which means that you cannot explain the 20th century warming without human contribution. But this assumes a very important assumption, which, as I will show you, hopefully, is not correct. That assumption is that there is nothing else to explain the warming. Nothing else contributed towards the warming. This is basically the standard picture. You see, this is what the IPCC is basically selling us. We can simulate the climate. We enter the different changes in the radiative forcings, which you see on the left. There is the anthropogenic forcing. There is the effects of volcanoes, and many other things. On the right, you see, on the top, you see the observed temperature in black. And in red and in the mustard-colored spaghetti plots, you see many realizations of global circulation models which fit the data. The next thing that you do is remove the human contribution, which is what you have at the bottom right, and you find that without the human contribution, you cannot explain the 20th century warming. Therefore, human contribution is necessary to explain the 20th century warming, and the climate has to be sensitive because we know what is the change in the human contribution, and therefore the climate has to be sensitive in order to explain the rise in the temperature. Okay, done deal, let's sign a Kyoto agreement and go home. Not so fast. As I said, it assumes that there's nothing else. Okay, so let's move to the next slide. Okay. Now, this is the, I think, three important questions which are related to each other, which we often hear, and I just want to make a little bit some order in them to understand how they're related, and in particular understand why, I think you now understand why solar activity is shunned, why the IPCC is doing its best to ignore the evidence that the sun has a large effect on climate. The most important question in climate science is what is Earth's climate sensitivity and by how much the temperature is going to increase over the 21st century. A related question is whether, and you see that on the top and the bottom right, is whether the temperature increase over the 20th century is primarily anthropogenic. If it's primarily anthropogenic, it means that we need a large climate sensitivity in order to relate those changes in the energy budget into the temperature increase. And that is related to another question, which is whether the sun or other natural drivers have an effect on the climate. Okay, so these are three related questions, and the standard answers that you will hear if you open the IPCC scientific report is that the temperature is going to increase by a lot because the sensitivity is high, most of the warming is anthropogenic, and there are negligible natural contributions to climate change over the 20th century. Okay, move ahead. Hence, those things are related. The sun is related to what will happen in the 21st century, and which the reason it is shunned. Okay, let's go to the next slide. Okay, this is now complicated. What I will try to, build another two. Okay, what I will try to show you is, first of all, the sun is important. About a half or maybe a third of the warming is human because we do change the climate. And the other thing, the main component is maybe half or 2/3 is the sun. The sensitivity is low, and therefore the temperature increase over the 21st century for a standard scenario will meet the 2-degree goal of the IPCC. Okay, so now I will try to show you why each and one of those things is correct. So let's begin by seeing that empirical evidence suggests that the climate sensitivity is low. Okay, so this is an example. It was pointed out by Richard Lindzen, which you saw interviewed by Andrew Bolt, the guy with the Australian accent. That's Andrew Bolt. The guy with the Brooklyn accent was Richard Lindzen. He pointed out to the following interesting point. If you look at how Earth's climate responds to changes in the volcanic eruptions, if you have large volcanic eruptions, you can eject material and have it stay in the stratosphere where you block solar light, you reflect the solar light, and therefore you reduce the energy budget for several years, so you should reduce the temperature on Earth. What he has pointed out is that the Earth's response to it is on the low side. In fact, if you look, the typical climate models predict that a typical decrease following the large volcanic eruptions like Pinatubo or Krakatau should be between 0.3 to 0.5 degrees. But if you look at the average decrease in the global temperature following large volcanic eruptions, it's only typically 0.1 degree. What does it tell you? It tells you that climate is not very sensitive. It's less sensitive than what you are being told. Next slide. Okay. On a different time scale altogether, on geological timescales, we have variations in the amount of CO2 which can be as much as a factor of 10. For example, 450 million years ago, we had 10 times as much CO2 in the atmosphere. Now, if CO2 has a large effect on the temperature, we should see that in the paleoclimatic record. Do we see that? No. At the bottom, you see a reconstruction of the temperature using geochemical methods. At the top, you see a reconstruction of the CO2 in the atmosphere. It's in a logarithmic scale because the variations are so large. Do you see a correlation between the two graphs? You don't. I mean, you're allowed to say yes or no. I mean, okay. I don't see any correlation. Maybe some people could, but I cannot. The lack of correlation between the two can actually be used to place an upper limit on the sensitivity of Earth's climate to changes in the CO2. This upper limit is the lower limit of the IPCC 1.5 to 4.5 degrees. Okay, so this thing actually tells you that the climate sensitivity should be somewhere between 1 to 1.5 degree increase per CO2 doubling. Okay, IPCC range, this data tells you it's somewhere like here. Okay, next slide. You might say, just a second, I saw Al Gore's movie, The Inconvenient Truth, and in that movie he has showed us this graph. How many of you have seen this movie? Quite a few. Okay. Now, you remember he even went up on a crane just to show us that the CO2 is increasing and all that. But what is this graph? What you can do, you can dig ice cores in Antarctica and in Greenland and measure, as a function of depth, things like the amount of CO2 trapped in bubbles, so you can reconstruct the CO2. And using geochemical methods, you can also reconstruct the temperature. So the two graphs that you see on the right, one is the CO2. I think it's the bottom one, well, I cannot see very well. And the top one is the temperature. And you see that they correlate very well, right? So you can tell me, aha, just a second. You showed us that there's no correlation between CO2 and the temperature. But here we see a wonderful correlation. So CO2 affects the climate. In fact, Al Gore in his movie, and if he was in his movie, then it must be correct, said that, what now? Okay. Said there's a very complicated, he said it actually in a deep voice because he wanted to sound authoritative. You see that there's a very clear correlation. We know that obviously there's a complicated relation, but we see that when there is more CO2, the temperature is higher. Why? Because he wanted to make us think that it is temperature affecting the CO2, right? Not necessarily. Maybe it's CO2 affecting, maybe it's, what did they say in a second? Yeah, CO2 affecting the temperature. But it could be the opposite, that the temperature is affecting the CO2, right? If we look at the next slides, we see an example where if you look at ice cores with a higher resolution than those that Al Gore has shown us, you actually find that the CO2 tends to lag behind the temperature. Namely, we definitely see that the temperature affects the CO2. Those ice core measurements don't tell us anything about the opposite relation, about how much the CO2 affects the temperature. There should be some relation, but those ice cores don't tell us anything about it. Okay, so you might ask, so why is the temperature affecting the CO2? Okay. It's unrelated to global warming, but it's an interesting question. And the answer is that most of the CO2 that you have in the ocean atmosphere system is actually CO2 in the form of carbonic acid in the oceans. And this equilibrium between CO2 in the atmosphere and carbonic acid in the oceans depends on the temperature. And when you heat the climate system, you change this equilibrium such that you release CO2 from the oceans and into the atmosphere. That's all. It's exactly the same thing you have in a Coke bottle. Has anyone forgot a Coke bottle in the car on a warm day? Okay, it's the same effect. Okay, next slide. Now, on very short time scales, we see again that the evidence is there to suggest that the climate is not very sensitive. Since the 1.5 to 4.5 degree increase has been there through all of the IPCC reports, except for the, not the last one, but the one before, it means that the predictions which were made in the first IPCC report in 1990 should still be valid. But what has the temperature done since the first IPCC report? It has increased, but significantly less than the predictions. Okay? It basically scratches the range of predictions from the bottom. What does it tell us? It tells us that most likely the climate is not very sensitive. Next slide. Okay, so to understand a little bit why people cannot predict what the climate sensitivity is, we have to understand a little bit what's the so-called greenhouse effects. I put quotation marks because greenhouses don't heat with the greenhouse effect. Okay, it's a misnomer, but there are many misnomers in life. Okay, so go back, well, take out the CO2. Oh, okay, no CO2. This is Earth's atmosphere, we get the shortwave yellow radiation coming from the sun. Some of it is reflected, but the most part, it reaches the surface. Now, the system on long timescales has to be in equilibrium, which means that the surface temperature has to be such that the radiation coming back to space at the top is equal to the amount of energy that penetrates the system. But because the emission of the thermal energy is in infrared and the atmosphere is mostly opaque in the infrared, what happens is that the surface cannot emit the radiation directly. It has to emit it, and it has to transfer through the atmosphere by various means, by radiation and by convection, by motion of material. So what happens is that even though the temperature is such that at the top is such that you radiate the same amount which is penetrating into the climate system, the temperature at the bottom has to be higher so that we can advect from the surface to the top this energy. This is what's called the greenhouse effect, the fact that the surface has to be at a higher temperature than the top. Add the CO2 now. We added the CO2. We now made the atmosphere more opaque. As a consequence, for the same surface temperature, the amount of energy leaving the Earth system is now reduced. If it's reduced, it's now not in a balance anymore. And if it's not in a balance anymore, what will happen? It will heat. So the surface will now heat. Okay, heat. Oh, now it's heated. It will heat to the level for which the emission from the top now is equal to the shortwave radiation penetrating the system. This is the greenhouse effect. However, Earth's climate is more complicated than that. If we didn't have anything in addition, what would happen is that we know that we would roughly change the energy budget by, say, 3.7 watts per square meter. But the Earth's climate system is going to change in addition to that. If we heat the surface, if we heat the oceans, we will evaporate water from the oceans. So we'll have more water vapor in the atmosphere. But if we have more water vapor in the atmosphere, water vapor is an excellent greenhouse gas. We will block more of the radiation. So we will get more greenhouse effect, and therefore we will heat the surface even more. Okay, but what happens if we have more water vapor in the atmosphere? We have also more clouds. And clouds can heat, clouds can cool, clouds can do a lot of things. And people really don't know by how much the cloud cover is going to change if you change the energy budget by a given amount, the temperature by a given amount, or the water vapor by a given amount. So all the global circulation models basically have the cloud cover described with a recipe. Now, one global circulation model can have one recipe for cloud cover, and therefore get one climate sensitivity. Another model can have another recipe, and you will get another climate sensitivity, because the feedback through clouds is going to be different. Okay, so the reason we don't know how to predict a climate sensitivity with global circulation models is because we don't understand clouds well enough. We cannot predict by how much they're going to change. Okay, so all the climate models, climate models are excellent for a lot of things, such as predicting the weather on timescales of days and a lot of other things. One thing they are not good for is predicting climate sensitivity. Okay, next slide. This is just a little bit technical. It's just to show you that what I said is correct. You see on the y-axis, you see the climate sensitivity of different models that existed in 1989. And at the x-axis, you see the feedback through cloud cover. Now you see that all the models sit very close to a single line. That tells you that the x-axis, namely the feedback through cloud cover, is the dominant parameter governing the feedback and therefore the total climate sensitivity. We don't understand clouds. Next slide. Okay, so we understand that the climate sensitivity is low, and we understand why people with global circulation models, and therefore the IPCC that is using global circulation models, cannot actually use it to predict the climate. Now, the other thing I wanted to demonstrate is that the sun has a large effect on climate. So let's see the effects. Okay, this we don't have to dwell into. The sun is variable. You saw that in the first, in one of the presentations before. It flips magnetic polarity every 11 years. And it does a lot of other things. With these changes, it changes the number of sunspots, the strength of the solar wind. It changes the flux of cosmic rays, which were talked about before, and all that. Now, the really interesting thing about solar variability is that in addition to the 11-year solar cycle, you have also very long-term secular changes in solar activity on timescales of decades to millennia. And those things, as we'll see, can affect the climate. Next slide. Okay, so what you see here is probably the nicest piece of evidence showing you that the sun has an effect on climate. What you see at the top is carbon-14 from tree rings. Carbon-14 is formed by cosmic rays hitting the atmosphere at the top. But cosmic rays, as I said, are modulated by solar activity. So the top graph is basically showing you a proxy of what the sun is doing. The bottom graph is oxygen 18 from stalagmites in a cave in Oman. Why is that a climate proxy? Because water with oxygen 18 is heavier than water with oxygen 16. So what happens is that the evaporation rate from the oceans is different for the two types of molecule, for the same molecule with the different isotopes. But this ratio is temperature dependent. So what happened is that the isotopic composition of the rain, in this case falling in Oman, in the monsoon waters in Oman, is a proxy of the temperature in the Indian Ocean in this case. So at the top you see a proxy of solar activity, at the bottom you see a proxy of temperature in the Indian Ocean. Do you see a correlation between them? Yeah, we see. Yeah, there's a very good correlation. Next graph. This is something similar from the Northern Atlantic. Again, we see the carbon-14, but we also see something else. We see, at the bottom right, we see cores dug from the bottom of the sea. And what happened is that we get annual depositions of what's called ice-rafted debris. If you have a colder winter, you'll have icebergs floating further south, melting and leaving their ice-rafted debris further south. So if we look at cores dug from the ocean floor, we can see whether it was colder and we had more ice-rafted debris, or warmer and we had less ice-rafted debris. In 1910, it was relatively cold. The sun was actually not very active. And we could have icebergs float further south and heat and cause very large debris. In fact, a Titanic-sized debris. Right? 1910. It was cold, so we had icebergs floating further south. Okay, so again, do you see a correlation between the two graphs? Yeah, we see. It's not as beautiful as before, but still, it's statistically, it's very significant. Okay, this is in fact the first such correlation in modern times that people claim between solar activity in the top and, in the bottom, and in this case, the severity of winters, namely a climate proxy in the top. And you see that over the past 1,000 years, there's a correlation between, in this case, climate in Northern Europe and solar activity. You see that in the latter half of the 17th century, at the bottom, we see that there was a lull in solar activity. There were almost no sunspots measured. And in the top, we see that it was very cold in winter. It was the peak of the Little Ice Age, or the Nadir, I should say, because it was bad times. On the other hand, in the Middle Ages, the solar activity was very high. There were, in this case, you can see a lot of auroras in Northern Europe. But it was also warm, and Vikings could circle northern Greenland and map it because there was no ice there back then. Is there ice in northern Greenland today? In summer? Yeah, there is. And Leif Erikson could actually travel to Newfoundland. What? Yeah, he was a newfie. Okay, makes you think. That's maybe, okay, no, I won't say newfie guys. Okay, next slide. Okay, this is another correlation, this time for the past century, and it's not with temperature or proxy of temperature. What you see here in red is solar activity. You can see the 11-year solar cycle. In black, what you see is the rate of change of the sea level. What it tells us is that every time the sun is active, the oceans are expanding. On short timescales, most of the change in the sea level is thermal expansion. Okay, when the sun is less active, the oceans are getting colder, they're shrinking. Okay, they suffer from shrinkage. Do you see a correlation? You see a correlation, of course. This correlation can now be used to, because we can now see by how much the oceans are expanding and contracting, we can quantify the solar forcing. We know by how much the energy budget on Earth changes when the sun is more active or less active. And this value is, we'll move to the next slide. Sorry, this is a more recent result showing that this correlation continued. Next slide. What you see here are different estimates. You saw the tide gauges, which is one estimate, for what is the change in energy budgets over the solar cycle. Okay, so you can look at the change of the sea surface temperature. You can look at the actual heat in the oceans. You can use altimetry data and so forth. All of those give you that the change in the energy budget is about 1 watt per square meter over the solar cycle. On the other hand, do you see the small points on the bottom right? This is the change in the solar irradiance. This is how much we would have expected if the sun's effect on climate would only have been changes in the total solar irradiance. This is what the IPCC says it is taking. Actually, it's even less than that, because from report to report, they downplay the effect of the sun even more. So in the last report, they said it's between 0 and maybe half this value. Okay, so this is what the IPCC is taking for the sun. We have direct evidence that it's much larger. Okay? This is how much they should have taken, and the little error bar is how much they actually take. Next slide. Okay, so we've seen that the sun has a large effect on climate, and we understand what it means for climate change. It means that there is another contributor towards climate change, and that is the sun. It's not taken into account, and you should. And when you do model it, you find that everything is consistent with the low climate sensitivities. I will show you in a second. But you can ask the question, just a second, we see this link. We are very curious people, right? We want to know where it comes from. So I'll tell you what this link is, because this is actually one of the things I research. This link is, we saw the link or the correlation between, say, carbon-14, which we used as a proxy for solar activity, and climate records. But it turns out that this carbon-14, which is formed by cosmic rays, or namely these cosmic rays, are not only the proxy for solar activity, but they are actually the link which links between between solar activity and climate variations. Next slide. At the bottom right, you see a correlation between the cosmic ray flux and the cloud cover. And so this is the first empirical evidence showing you that it is the cosmic rays affecting the climate through modulation of the cloud cover. Next slide. Okay, this is the link. So the link is through clouds, and how does it come about? We have the sun. The sun has a solar wind. We also know about the cosmic rays, these high energy particles which come from supernova remnants from outside the galaxy. The interesting thing about the cosmic rays is that they are the dominant source of ionization in the atmosphere. Here we have maybe ions coming from radon emanating from the concrete. Don't be shocked. But if you go outside, most of the ions, or almost all of the ions, are formed by these high energy particles. So when the sun is more active and the solar wind is stronger, less of these particles can reach the Earth, and therefore the ionization is lower. So the amount of ions is reduced when the sun is more active. We now know that several things happen. When we have more ions in the atmosphere, we form more condensation nuclei, more few nanometer sized particles, which later grow to become the cloud condensation nuclei. These are larger sized particles, which serve as surfaces upon which we can condense the water vapor when we form clouds. So what happened is that when the sun is more active, we have a stronger solar wind, less cosmic rays, less ionization, we get less formation of, or less nucleation of these condensation nuclei, and also less growth of these condensation nuclei to cloud condensation nuclei. So we have less of those cloud condensation nuclei. Now, when we then form clouds, when we reach 100% humidity and want to condense the water vapor, what happens is that we get clouds which are less white. They're less white because they reflect less of the sunlight, because there's less surface to reflect, and because it leaves, those clouds live shorter. So if we have clouds which are less white, we reflect less of the sunlight. So what will happen? We will warm the planet. Okay? More active sun, stronger solar winds, less cosmic rays, less ionization, less nucleation of condensation nuclei, and less growth to large cloud condensation nuclei, clouds which are less white, reflection of less sunlight, and therefore a warmer planet. And today we have empirical evidence showing that everything takes place in this chain. Next slide. This is an example for such evidence. Over timescales of days, we can get gusts. You saw in the movie before, you saw gusts, you saw coronal mass ejections, like those magnetic loops closing, and then you get a gust in the solar wind. This gust in the solar wind can later reduce the flux of cosmic rays reaching the Earth. So you see in the red a reduction in the cosmic ray flux reaching the Earth. As a consequence, you see in the first panel on the left a reduction in the number of aerosols over the oceans. And then 3 different cloud data sets shows you that you have a similar reduction in cloud parameters as a response to these gusts in the solar wind. On very long time scales, you can do something else. You can reconstruct, you have variations in the cosmic ray flux which are not associated with changes in solar activity, but they're associated with the fact that the environment around the solar system changes. Sometimes we have more supernova remnants next to us, and therefore more cosmic ray flux variations, and sometimes we have less. The largest source of cosmic ray flux variation on geological timescales is the fact that every so often we pass through spiral arms of the galaxy, and we witness more supernova remnants, and therefore cosmic ray flux acceleration. So at the top, you see a reconstruction of the cosmic ray flux based on iron meteorites. And at the bottom, you see a reconstruction of the temperature by looking at oxygen 18 in fossils. Okay? Do you see a correlation between the two graphs? Yeah. In fact, you can reconstruct and see that there are 7 oscillations in the cosmic ray flux over the past billion years. And over the past billion years, you also have 7 occurrences of ice age epochs each time we passed through a spiral arm and we had more cosmic rays. Another thing takes place when we roam the galaxy. In addition to our passages through the spiral arms, we also move up and down through the galactic plane. And at the galactic plane, the cosmic ray flux is higher. What this implies is that we should see a shorter timescale variation in the temperature. Do we see that in the data? The answer is yes, otherwise I wouldn't have bothered you with it. We should see a 32 millennial oscillation with a given phase, and the data shows you exactly that. What you see here is on the y-axis you see the temperature, the time over the past half billion years. On the x-axis you see 2 cycles, or you see the data folded over 32 million years, and just see 2 copies so it will be clear. And the color tells you whether it was cold or hot. After you remove the 145 million year longer time scale. So this is like a secondary oscillation, which has a very clear 32 million year oscillation in the temperature, which agrees in phase and in period with what you would expect from the vertical oscillation through the galactic plane. Now, a keen-eyed observer will see that the best fit is actually not a straight line, but there's also another modulation in the 32 million years. This modulation agrees in phase and in periods with the radial motion of the sun in the galaxy. When we're closer to the center, the density of the plane is higher, so we're oscillating faster. When we're further out, we're oscillating slower. So in fact, the cosmic ray flux variation, or the cosmic ray effect on the climate, links between our galactic motion and climate on Earth over geological timescales. Okay, next slide. More evidence. Press it again. Okay, the fact that more ions nucleate small particles was measured directly in the lab. On the left, you see the first experiment that took place in Copenhagen and was published in 2006. You see that when you increase the ion ionization rate, that's the x-axis, you nucleate more particles, that's the y-axis. This experiment was repeated at CERN, and they basically saw the same thing, only with higher quality data because they have more money to run the experiment with better conditions. Next slides. Okay, we also measure, press it again, we also measure the next step. Press it again. You can see if you just increase the nucleation, then the number of aerosols that you get as a function of size will be diminishing when you look at larger and larger aerosols, and that's because as the aerosols grow, they can actually be eaten by larger aerosols. But on the right, you find that if instead of just injecting, you increase the ionization, you get that aerosols survive to larger sizes as well. So there are two effects here. One is that they nucleate more, and the other one is that the ions help the aerosols survive the growth from this size to, well, it's from 3 nanometers to 50 nanometers, which is still very small, but enough to allow condensation. So we see things in the lab. Next slide. The fact that when you have more cloud condensation nuclei, the fact that this affects the properties of the clouds is very easy to see. All you have to do is Google ship tracks, and you'll see images like this one, like this one. Yeah, like this one. Here you see the marine layer opposite of California and Oregon, and you see also a forest fire. But those, what appears like contrails, it's not contrails, it's ship tracks. Sheep, because they travel in international waters, they can burn the dirtiest fuel possible. So they form a lot of exhaust particles, and those exhaust particles serve as cloud condensation nuclei. So you see that by playing with the density of cloud condensation nuclei, you can affect the cloud properties. You can make them whiter. Next slide. Okay, so let me start to wrap up. The main, or the standard picture is the following. We have the anthropogenic forcing affecting or the primary or the only, the anthropogenic being the main driver over the 20th century. Because we know that the temperature increased by about 0.8 degrees over the 20th century, we need a relatively high climate sensitivity in order to explain this temperature increase. But a high climate sensitivity will also tell you that the temperature increase over the 21st century should be high as well. Now, what is the evidence supporting the high climate sensitivity? There is none. It's a figment of the imagination of the global circulation models. What happens in reality? In reality, we have another very important climate driver, and that is the sun. This means that the total energy change in the energy budget over the 20th century is much larger. And if it's much larger, then in order to explain what has been going on over the 21st century, we now need a low climate sensitivity. A low climate sensitivity will then tell you that a given emission scenario over the 21st century will be small. Is there evidence to support this low climate sensitivity? Yes, if you look at the empirical data, all the empirical data shows you that it should be small. Next slide. Okay, you can actually build a model which takes the sun into account, which looks like this. Next slide. And then you can find that when you take the sun into account, you can fit the 20th century much better than global circulation models. On the left, you see our fit to the 20th century. The difference at the bottom is the residual. It's typically 0.1 degree or less. On the right, you see typical fits done by standard global circulation models that don't take the sun into account. And their residuals between model and measurements is much larger, typically twice larger. Why? Because they don't take the sun into account. Now, we can take the fits over the 20th century and integrate forward in time, assuming we know what the emission is. So in this case, you see the predictions based on a standard emission scenario and run many realizations, taking into account realizations for what the sun might do, what the volcanic eruptions could be, and so forth. So you see this spaghetti plot. And then you can do that and compare to what the IPCC predicts, which is this. Okay? So because the climate sensitivity is low, the temperature increase over the 21st century is going to be low as well. Okay, so this is the main three questions and answers that the IPCC gives. High climate sensitivity and so forth. This is the real life. The climate is not sensitive. There's a lot of natural contribution to temperature change over the 20th century, and it all goes hand in hand with the fact that the sun is an important climate driver. And I think with this, I'll end. Yeah. Yeah.